Welcome to a lesson with Dr. Powell. Okay, so in the last video, we found the critical point, and we're going to test it to see if it represents a maximum or a minimum. So let's think about this for a little bit. In order for it to be a minimum, what needs to happen? So here's a point there's a point on the surface. And let's think about what happens as we move out just a little away from that point. So at this point, the surface is relatively stable. It's instantaneously just flat at that point and not going up or down in the z direction at all. Now, as we move away, though, for it to be a minimum, we would like the graph to be increasing. So as we move just a little bit away in any direction, we'd like the graph to be bigger. In fact, if we move a little bit away, we would like the derivative to be showing. If we're just moved small enough away, we would like the derivative to actually be such that it's giving positive rises in every direction. So to give a positive rise for a run in this direction, just think about the derivative could be thought of as a vector. In this case, like fx, fy. And to get the rise, you basically take the dot product of that and the direction you're heading, or your run, the run that you're heading, that vector. And if you do that, you want that dot product to be positive in order for there to be a positive rise, which means that the gradient vector basically needs to be pretty much in a similar direction to the direction you're heading. So the direction of the run and the direction of the gradient need to be similar as you're moving away from this point. Okay, so the derivative at first, right at this point, is actually 0, 0. Then as we move a little bit away, move in this direction, the derivative will change. But whatever it is, at this point, it needs to be in a similar direction to the direction that we actually went, just barely went. So these need to basically be similar in direction. Let's think about how that's going to work. The second derivative, so the derivative of the derivative, tells us how the derivative is changing. And we want how that works to reflect this change, that basically as we move out, the gradient is going to be roughly in a similar direction as we move away. So that the gradients as we move away, here's a picture, the gradients themselves will look roughly, might kind of be sway a little bit, but that's okay. So they might not be exactly in the same direction as the arrows, but you're going to have a positive rise, so the dot product will be positive. Okay, so that's kind of the picture that we want, the gradients, but the gradient right here at this point is just a 0 vector, and then here maybe the gradients are kind of like that as we move away. So this is what's going to guarantee a minimum. So let's look at this case and think about what we need for that to occur. So the second derivative, let's look at that. That's how the derivative changes. We want it to reflect this. So let's take the derivative of the derivative. So to do that, let's think about the derivative as having two outputs, okay, an fx and an fy. And what we're going to do is, so we have two outputs, and then for every input, we have an x and a y. We'll be taking a derivative of that. So basically, we're going to take the derivative of the derivative itself with respect to x, then with respect to y. Just like we did the function with respect to x, function with respect to y in order like this. We do the same thing here, just kind of turn this as a column and say derivative of this with respect to x, derivative of this with respect to y. So this becomes like that. So just the derivative of this with respect to x, then y, then x, and here just y's we add on right there. Okay, so it looks something like this. All right, so this is the matrix that represents the second derivative. So when we put a run into this, then what comes out is a vector, and that vector is going to be how much the gradient will have changed. So the amount that we want the gradient to have changed, actually, well, if the gradient starts at 0, then the new destination of the gradient is how much is changed. 0 to there, I mean, that is what the change is. So basically the new gradient, what we want is actually going to be the output of this for any run. So whatever run we put in here, suppose it's like u1 and u2. Okay, so this is just a vector that's representing run. What we get out, we're going to get out something. And whatever we get out is going to be the new gradient kind of basically at that spot away that we've moved. And we want this to be in line with this. So we want the dot product between these two things to be positive, basically in the same direction. Okay, now let's think about a way that we can actually get that. What if from this point we just have two different directions? Doesn't matter if they're 90 degrees or not. It could be skewed, or the directions could be, you know, these two or something like that. Let's just look at this picture though. So if you have these, you have two different directions, and let's suppose that the matrix, what it does is in this particular direction, what it does is it does better than just make the gradient just be just a little bit off of that direction. It actually makes it in line with that direction. So if we can find two directions where the matrix actually makes it in line and in line over here, then what we can do is if we have any other vector, we can take this as a sum of maybe a multiple of this and a multiple of this one. So a sum of these two, where it's doing that, it's actually going to basically pretty much preserve the direction of this as well, just, you know, maybe be a bit off, but it'll be a positive dot product. Kind of a very nice idea. If we can find two such directions, this matrix, which is also called the Hessian matrix, sometimes takes on a special name such as positive definite or something like that, always making these positive dot products with any vector in any direction, the result versus the input. Kind of a neat idea. So kind of preserving the direction. So all we really need to do is find these two different directions. Where when we take the matrix and we input a run in that particular direction, the matrix is going to behave just like a scalar. And we're going to take a look at a scalar multiple of that. Okay, so in the next video, we're actually going to work through the computational part to actually find out if this is true, if there are such directions, and if there are, what the scalar multiples are. This is important because if the scalar multiples are positive, that's what we want, because that's going to preserve direction. If the scalar multiples happen to be negative or non-existent or something, then we wouldn't have this situation. So what we want is some that are, if we have two that are positive, then we're going to have this minimum thing happening. If we have two directions with two different scalars that are negative, then well, then in that case we'd have a maximum. So stay tuned. Next video, we'll work out the computational details in this particular example of how to do that. Thanks for watching.